thanks everyone for turning up today. Today we've got a couple of presentations with an Australian theme, hence the new time for today's meeting. We've got Charuni Pathmeswaran from the University of New South Wales, who did her PhD research at the University of New South Wales. She recently completed her PhD earlier this year in February on the topic of understanding co-occurring terrestrial and marine heat waves. She's now working as a knowledge exchange broker for the Bushfire and Natural Hazard Research Centre for the New South Wales Department of Planning and Environment. And I'd like to pass over to you, Charuni. Just start when you're ready. Thanks.
Thanks, Cass. Start sharing. Is that looking okay? And can you hear me okay? Okay, thank you. So hi, everyone. Thanks for giving me this opportunity to talk today. I would first like to begin by acknowledging the traditional custodians of the lands that we meet on today. So I'm dialing in from Wangal land, and I would like to pay my respects to elders past, present, and emerging. And I would like to also extend that respect to any Aboriginal or Torres Strait Island people who may be joining this webinar today. So like Cass mentioned, this is work that I did as part of my PhD at UNSW Sydney, which I did with Alexander Gupta, Sarah Perkins Kirkpatrick, and Melissa Hart. And so today I'm going to talk to you about exploring potential links between co-occurring terrestrial and marine heat waves in Australia. So to give you a bit of background, heat waves are prolonged periods of excessive heat. They impact various sectors, including public health, infrastructure, agriculture, and transportation. But they're not only limited to land. Marine heat waves have been getting a lot of press lately. They can negatively impact marine ecosystems and have negative repercussions on socioeconomic systems. And so, although a lot of research has been done on terrestrial and marine heat waves independently, not a lot has been done on trying to see if there is any potential link between the two. But very recently, there has been an emerging interest in co-occurring terrestrial and marine heat waves. There have been some regional studies that have focused on these co-occurring events in Southern Africa, Southwest Atlantic, and also the Tasman Sea. So what really caught our eye when we were starting this research was this particular study that focused on the South Atlantic marine heat wave and the co-occurring terrestrial heat wave over South America in 2013-14, done by Rodriguez et al. In 2019, where they focused on these events and they tried to understand if there was a common driver that was responsible for driving these co-occurring events. And what they found was that there was this high pressure system that was straddling over the ocean and on land, which led to low clouds. There was more shortwave radiation coming through, reduced winds. And so there was this buildup of heat in the ocean as well as on land at the same time. And so this is what really set the stage for our research. And we were keen on exploring a similar phenomenon in and around Australia. So to do this, we used the NOAA OISST data set to look at the daily sea surface temperature. We also looked at the ERA5 reanalysis data set to look at daily maximum temperature. And we looked at ocean heat content and mixed layer depth from the Access S2 outputs. So we first had to define the terrestrial and marine heat waves. And to do this, we followed the Perkins and Alexander framework, where a terrestrial heat wave is defined as where the daily maximum temperature exceeds the 90th percentile for at least 3 consecutive days. And similarly, we followed the Hobdet framework, where a marine heat wave is defined where the daily sea surface temperature exceeds the 90th percentile for at least 5 consecutive days. Now, once these events were identified, we then had to define what a co-occurring event was. And so for defining this, I'll explain it using this graphic here. So the top panel looks at sea surface temperature and the bottom panel looks at surface air temperature. And in both these panels, we've shown the mean climatology in green, we have the threshold, which is the 90th percentile in red, and we have the daily temperature values in black. And so what I've marked in blue are the marine heat waves, and then in yellow in the bottom panel are the instances where there was a terrestrial heat wave. And so whenever there was an overlap between a marine and a terrestrial heat wave, we show that in this green bar here, and that's what we term as a co-occurring terrestrial heat wave. And the other thing to note is that since marine heat waves generally tend to last longer than their terrestrial counterpart, we break it up into their build-up and decay phases just for better understanding of these events. So this is how a co-occurring event was defined. So the first question we wanted to answer was, did the likelihood of terrestrial heat waves increase in the presence of a marine heat wave? And so to quantify the likelihood of co-occurring heat wave days, we came up with a ratio called the occurrence ratio. This is essentially the ratio between the co-occurring heat wave days and the standalone heat wave days. And we do this for the whole coastal belt around Australia. And then to see if this likelihood is significant or not, or if it's happening just by chance, we did a Monte Carlo analysis consisting of 10,000 simulations. And how we did this was, so for each simulation, I kept the marine heat wave time series intact, but each time I would randomize the terrestrial heat wave time series. And with each randomized time series, I would then recalculate this occurrence ratio. And I would repeat this for all. So I would do this for pairs of coastal cells and adjacent marine cells. And I would do this for the whole coastal belt around Australia. So this is an example. So this is just showing you what I've done for a given pair of cells. So this PDF here is the PDF of the randomized distribution. So the Monte Carlo simulations, all 10,000 together will give you this PDF. And then I've also showed the 99th percentile of that distribution. In red, we have the observed occurrence ratio. So you can see that this observed value sits way outside the randomized distribution that we would expect if it were happening just by chance. Then to explain this value further, this occurrence ratio of 0.82 essentially means that co-occurring terrestrial heat wave days occurred 82% of the time compared to standalone terrestrial heat wave days. And so when we compare it with the Monte Carlo distribution, we would expect this value to fall somewhere between 13 and 34% within that distribution. And so this suggests that this occurrence ratio is highly unlikely to occur by chance. And then so we repeated this for the whole coastal belt of Australia. And then we wanted to see how much does this observed occurrence ratio deviate from that random distribution. And so to come up with this, we then came up with this term called the exceedance ratio. Now, the exceedance ratio is essentially the ratio between this observed occurrence ratio and the 99th percentile of the distribution that we would get if we have this randomized PDF. So this was then repeated for the coastal belt of Australia, but not just the outermost coastal belt. We went inland as well, up to about 1.5 degrees inland. And so a quick recap, if the exceedance ratio equals 1, it means that your occurrence, the observed occurrence ratio, is equal to what you would expect if it were a randomized distribution. So any value that exceeds 1 indicates that there's a significant increase in the terrestrial heat wave days in the presence of a marine heat wave. And that's what we're seeing all around Australia. And in some regions, we see that this exceedance ratio drops off. And this suggests that it's more for local process that's driving these events. Whereas in certain other regions where you find that the exceedance ratio is more or less the same, it goes to show that larger scale processes are in play. So once this statistical analysis was done, we then wanted to see if there are common synoptic drivers that are contributing to the generation of these co-occurring heat waves. And so to do this, we focused on 3 case study locations. So we looked at Townsville in Queensland, which is the northeast coast of Australia. We looked at Ningaloo off the northwestern coast of Australia, and down in Tasmania, we looked at Hobart. And so now I'd like to bring you, or rather for you to pay attention to these first and third columns here, the standalone terrestrial heat waves and the co-occurring terrestrial heat waves. If you look at them, you can see that the synoptic conditions are very similar to each other. The high pressure system sits in similar locations. The wind directions are very similar, and it's the same story for the other 2 locations as well. So what this suggests is that similar synoptic conditions are conducive to both kind of events, both the standalone as well as the co-occurring event. And so whether we see a marine heat wave or not really depends on ocean preconditioning, which essentially means the initial state of the ocean. So you might have the right weather systems that can drive a marine heat wave, but the ocean may be starting off at a very cold condition and may take a long time for it to warm up. So this is what we mean by ocean preconditioning. And to test this hypothesis, to sort of explore this further, we looked at 2 factors, and one of them was ocean heat content. And so again, if you look at the standalone terrestrial heat waves and the co-occurring terrestrial heat waves, these composite maps, again, so this was done for 7 days prior to the event, just because the ocean takes a longer time to heat up. So we wanted to see what the ocean heat content looks like in the run-up to an event rather than on the day of that event. And so what you see when you compare the co-occurring and the standalone terrestrial heat waves is that the ocean heat content is higher when there's a co-occurring event, that is when there's a marine heat wave as well. Similarly, we also looked at the mixed layer depth. And so when you compare the standalone and the co-occurring terrestrial heat waves, you find that although the difference is not as pronounced as the ocean heat content, you can still see that in some instances, the mixed layer depth is actually shallower during a co-occurring event. So there's shoaling and the water depth is much lower so that the heating can occur faster, and that can in turn result in a marine heat wave. So keeping this in mind, one thing that we had to note was that, so like I mentioned before, although, so the fact that we saw these similar synoptic conditions between co-occurring and standalone events suggests that similar synoptic conditions are driving these 2 kinds of events. So although we may have those right conditions, the ocean may not be warm enough for it to generate this marine heat wave, because it could be starting from relatively cold conditions, or the mixed layer depth is just too deep, and so it takes much longer for it to warm up. But it's a bit tricky to determine if this is what's happening, because marine heat waves by definition are periods of high ocean heat content, and the surface intensified heating would then lead to shoaling that mixed layer. And therefore, it's a bit tricky to say if these ocean conditions during the marine heat wave buildup are the cause of the marine heat wave, or are they actually a response to the processes giving rise to the marine heat wave. So this was something that we had to take note of, or rather acknowledge, when we were trying to explore the reasons why we were seeing a marine heat wave in some instances and we were not seeing in certain other instances. The other thing that we have to acknowledge as a limitation of this study is that, so for the interest of time, I've only shown a few of the factors, such as the pressure systems and winds in terms of probable driving mechanisms, but we also looked at other factors such as latent and sensible heat fluxes. We looked at shortwave radiation. So the way we looked at this was by using composite maps. And although those results can suggest that certain drivers are contributing to these events more than others, I think a more formal heat budget analysis is required so that we can make more quantitative statements about each factor and how they come into play in contributing to these co-occurring events. So that's another thing that I would just like to point out in this presentation. So to summarize the study, we did find a significant increase in the number of terrestrial heat wave days in coastal Australia when there was a marine heat wave present as well. And this increase remained at least 150 kilometers going inland. And so this suggests that these co-occurring events are influenced by things beyond processes that are occurring within a narrow ocean belt. And so the other thing, when we look at the 3 different case study locations of Townsville, Ningaloo, and Hobart, we find that these synoptic conditions that can drive a terrestrial heat wave in these regions are also conducive for warming the ocean. But although it can increase the likelihood of that marine heat wave, whether we see a marine heat wave or not depends on the ocean's prior state, and that can be better understood by looking at factors such as the ocean heat content and the mixed layer depth. And so that was also a very important finding because it was not just what was going on in the atmosphere in terms of the synoptic conditions, but also what the ocean really looked like. And so in a nutshell, if there's one thing that you can take away from this study, is that terrestrial and marine heat waves co-occur more frequently than we would expect if it were to happen by chance. So there is a significant increase in terrestrial heat waves when there's a marine heat wave. And large-scale synoptics can be conducive to both these coastal and marine heat waves. And the other thing we need to keep in mind now is that as marine heat waves and terrestrial heat waves are becoming more frequent and more prolonged, the chance for there to be an overlap between these events is also increasing. And that suggests that co-occurring heat waves can be more common in the future than we are seeing now. And so, yes, if you would like to get more information, these findings have been published in Frontiers in Climate last year. And I'm happy to take any questions today as well. So thank you.
Great, thank you, Charuni. It was really interesting. Mona, maybe we'll take a few questions if anyone has questions now, or maybe we'll leave them to the.
We usually ask question. Leave the question for the later.
Okay, that might be easier. In that case, we'll go to Nina Ridder now. So Nina was previously working also at the University of New South Wales for about 4 years from, I think it was 2019 to 2022. And then about a year ago, she started working at Suncorp, an Australian insurance company, and that was to continue on as a compound events researcher, looking at how that will influence insurance. And please correct if I didn't represent that quite correctly, please fix that. Nina, but I'll pass over to you now. Thanks.
Thank you. No, that was good, thank you. I'll just start sharing my slide. So yeah, as Cass mentioned, I'm Nina Ridder. I'm the Senior Climate Advisor at Suncorp Group Limited, which is an insurance group here in Australia, and we also have insurances in New Zealand. And I have to start, now it's not changing. Here we go. I have to start with this disclaimer, just it's my views, it's my opinions and my conclusions, and they are not necessarily representative for my employer because I don't want to have a very short career. So just a quick overview. At first, I'm going to give a brief introduction into insurance basics, how the insurance sector has determined that and now is determining risk. Just show very briefly work that I've done on compound events in Australia, and then I'm going to talk about compound events, how they impact insurances in Australia. So first of all, I think we're all familiar with the concept of insurance. So as the point of the insured. So basically, I'm the insured, or I have something that I want to insure. I go to an insurance company and I'm going to agree on a policy with them, pay them, and if anything goes wrong with whatever I've insured, like my house, if it gets hit by a tropical cyclone, for example, I get money from the insurer. So to make this profitable for the insurer themselves, they actually sign more than just one person, and that's what they then call a portfolio. So that's a mixture of insurance policies that they have with a bunch of people, ideally spread over a region, especially when it comes to natural perils insurance, so that not everyone gets hit all the time. Or at the same time rather, and you can actually make some profit, which is important for your capital and for your for your shareholders. So if we talk about natural perils, the insurance sector actually is very focused on specific natural perils rather than climatological hazards. What I always thought when I was a scientist, well, I'm still a scientist technically, even though it feels a little less so after I sold my soul to the insurance world. But so we look at specific natural perils, so tropical cyclones, flood, hail, storm events, and bushfires, and technically also earthquakes, but I left those out for, well, they're not really have anything to do with climate. So where's the difference between a hazard and a peril? Well, it's basically the hazard is the underlying factor behind a peril that leads the probability of an event to occur. So for example, when a forest is burning, the fire is the peril, whereas the dry vegetation that gave rise to this fire is the hazard. So traditionally, insurances determined policy prices by looking into the past, so historic events, and then ask the question, how often and where have they occurred? So we have the frequency of claims. That's important here. So we look into the past of our own data or data that we can get our hands off, and check, okay, how often have we seen a certain number of events and how severe were these events? So these claims that we've had. So this is a very statistical approach and very reliant on historical loss, as I said, and this only works if we actually have seen every possible event in the past. This is obviously not the case, and that is what the insurance world realized in 1992 when Hurricane Andrew hit the US. At that point, it had been quite calm in the area when it came to large or strong hurricanes. So it caught a lot of people, and especially insurance companies, by surprise, because they oversigned in this area and a lot of insurance companies went bankrupt. So this showed basically that the traditional approach of just going by past losses and treating them completely independent of the actual hazards that we are seeing or perils that are occurring, the physics behind these, that doesn't make sense. So since then, the insurance world or insurance companies have changed to so-called catastrophe models. The first time I heard CAT model and I Googled that, let's just say it didn't help a lot. I was very entertained, but it didn't explain what the insurance people were talking about. So I was just as clueless as before. So the CAT models basically look very familiar to us because most of us have seen the IPCC's definition of risk and the visualization of that. And that is exactly this. So you have the overlap of hazard, vulnerability, and exposure is your risk. In the insurance sector, it's not hazard, but we call it a peril. And we determine the contribution of this peril to risk by generating an event set based on physical models. Then the vulnerability is basically we come up with a damage function. So we map the intensity of the loss that we expect in accordance to different severities of an event and come up with damage function, which is quite an engineering-based approach here, so a little less familiar to climate scientists. And exposure, well, that's basically very easy for an insurance. We just go, okay, where do the people that we have policies with live? And then we just overlap that. So if we look into the perils or the event set generation, this is an example for tropical cyclones, which has been, well, historically the most explored CAT models, because they are the origin of CAT models, basically. And so what we can do is we can look into past events and randomly sample from the data set that we have and just generate wind fields from that. These wind fields are constructed from specific equations that we know linked to the central pressure, the radius, and so forth of the tropical cyclones. And we do that thousands of times. And with that, we get a range of possible events. So we don't only have the events that we know, but we get like thousands upon thousands of feasible representatives. And then for the severity of the events, so that is the vulnerability curves that we were that I mentioned earlier, we look into the type of property that we are insuring. So if we look on the right side, you see something like the X and Y axis is something that for an insurance company is very familiar. So you have an event intensity on the X axis, and on the Y axis is a function of the intensity of the event. We see the loss incurred. And the loss incurred is based on what the asset is, what it's made of. For example, what kind of roof tiles do we have? Do we have roof tiles? Do we have corrugated roof, and so forth? And how likely is it that we see damage to this building or the construction? On the left side, you can see that's for Australia. That's the building standard for and tropical cyclones. So that's another thing that you can take into account for generating the severity or the incurred loss due to severity. And so from that, so we have the large amount of possible representations of an peril. Then we map or use that to generate these damage curves or decide what kind of damage are we expecting. And from all these representations, these thousands upon thousands, we get a distribution of possible annual losses. And that gives us an idea of our risk as a whole. So I can't go into more detail because I am still very new to insurance, and quite frankly, before this, I was never interested in it. And even now, I prefer to stay at the physical science part of the whole exercise. So I hope this gives you a bit of an overview, but if you have more questions, I will try to answer them, but I can't promise. So when it comes to natural disasters, Australia and New Zealand, well, we've had our share in the last 4 years. So we've seen the most devastating floods last year in Queensland and New South Wales, which ended up with one of our top 2 insurance loss events over the past, or well, since the 60s, really, 1960s. Before that, we had the Black Summer bushfires, where prolonged dry and hot conditions caused unprecedented bushfires from their intensity and from the area that were burned. And just earlier this year, Auckland was hit by 2 events, actually, that together mounted up to a catastrophe that was that's the most expensive non-earthquake related catastrophe in New Zealand. So if we look into the most costly historical industry losses in Australia, I'm not sure if you can see, I hope you can read some of these at least, but it's basically, if we take out the earthquake one for Australia, which is again not what we're interested in this case, we see a lot of floods and cyclones, tropical cyclones and storms. And if we look at these, just the top 10 are almost exclusively or could be classified as compound events of some way or another. This data set is freely available. It's hosted on by the Insurance Council Australia, and this is actually an older version. They just recently released last month a newer version where the inflation values, the normalization was done by updated inflation values. These are the inflation values by 2017. But the flood that I mentioned is here on number 1, but it has to do with what kind of inflation correction you're using. It might be number 2 even. Anyway, insurance companies are aware that we have compound events. So we can ask the question, so where did compound events occur in the past in Australia? And that is work that I've done during my time at UNSW. And here we looked into 2 types of events. We looked into wet and windy events and hot and dry events. So wet and windy events like storms, where we know in Australia we have loads of them, and they're quite important for floodings and other damages. And we looked into hot and dry events, which are precursors for the bushfires. Again, we know in Australia we have a lot of bushfires and quite severe bushfires. And we used past observations, and for the wind data we used reanalysis, because we don't have reliable wind observations in Australia, or none that we had access to. And here we just went in for a simple peak over threshold and then empirically determining the probability of an event. So when we do that, we can derive a climatology, and so here it's shown in return periods or return frequencies, as I was corrected by an engineer at the last AMOS conference. On the left, you see hot and dry events co-occurring, and on the right, you see wet and windy, where the warmer colors show you that it is more likely, or these events occur multiple times per year, and then the colder colors mean they're less likely. And just to give you a reference, the Black Summer bushfires happened in the southeastern part of Australia. So I hope you can see my mouse. No, you can't. Nope. Can you see it now? Okay, I had it on the wrong screen. I'm sorry about that. So the Black Summer bushfires happened in this area, and you can see that we do experience prolonged hot and dry conditions in this area at least once, if not twice a year. On the other hand, for wet and windy events, we nicely see the tropical cyclone signature in the north and in the northeast here. Not quite sure why we can't see it around here in northern Queensland, but that is probably something to do with the wind data that we were using. So, as I mentioned earlier, I just presented hazard maps, which is not really helpful for insurances. But insurances are more interested in the kind of perils that were caused by this. So in order to look into that, this is very new work and still a little, well, it hasn't been peer reviewed, so I'm happy to take suggestions and feedback, critical feedback, if you realize something that is off. So what I did, I took the ICA catastrophe database, which includes the dates of an event, and I added a window around it for ±2 days, and I compared it to the data sets I have from my compound events from the observations. And then I divided Australia into states. And for each state, I then decided, okay, so if I have a catastrophe happening and the state that it is happening in experiences a compound event at any point, I say, okay, my compound event is linked to this kind of peril or this catastrophe. I hope that makes sense. So, and if I do that, in this case for New South Wales, so you can see up here, that's a state located in the southeast of Australia. On the left, you see the perils that coincided with hot and dry events, and on the right, those that coincided with wet and windy events. That doesn't mean that they were caused by these co-occurrences, but it's just they happened at the same time in the same 5-day window. So there is a chance that they are somehow related, even though a tropical cyclone and hot and dry events might not necessarily be a relation that you would expect. And it's probably not a relation that actually happens. It is more that it is a large state. So, and hot and dry events mainly occur in summer, which is also the tropical cyclone season. So that might just be a random coincidence rather than an actual correlation between there or causal. But overall, you can see what you probably expected. So for hot and dry events, we see the largest peril, the peril that has caused the biggest loss, are bushfires. And for wet and windy events, we see that basically every peril that occurred has something to do with the kind of storm definition that we have. East coast lows are, by the way, low pressure systems that cross over Australia, the east of Australia, that develop in the Tasman and then move over Australia. So it's just a specific type of storm, basically, a synoptic storm. Then just one more example for Queensland, where we have hot and dry events and wet and windy events here on the left and on the right, respectively. And here again, we see tropical cyclones, probably rather a signal of when hot and dry events happen rather than what they cause. And wet and windy events, not too surprising, it's tropical cyclones and flooding. So I intentionally didn't give you the exact numbers. As I said, here I use old normalization factor for the losses. So I left that out. But this data is freely available. So if you want the numbers, I'm happy to give it to you. I just didn't want to show it now and then later on be quoted. So, but she said this and that. So this is very early stages, as I said, and I did it for the other states in Australia as well. It just isn't that interesting. So I didn't want to bore you for too long. Just to give you an idea how we can match the hazards that we traditionally look at as climate scientists and try and link them to the perils that an insurance would be interested in, and how we can work on that, on lining that up a little better. So, and with that, I come to challenges for the insurance companies. So the insurance sector is well aware that compound events have the potential to be devastating and cause really damaging catastrophes. However, they're very rigid in the way they do it right now, because of the long-standing CAT models and also because of regulations, basically. So it is less easy for them to change something without having to go through a lot of processes and regulations with the overall governing body of insurances. So it would be helpful for them if we could express our work more in the peril kind of mindset rather than the hazard mindset. There has been work where insurances start to correlate different perils rather than hazards. not necessarily like at the same time or like multivariate, but multivariate in a sense of, well, in the selection of my whole country that I'm insuring, where do I see perils at the same time? I think I said the rest already without sticking to my slide. I apologize for that. So in conclusion, because I think I rambled on for long enough, I would like to advertise or advocate rather that there's more communication between insurances and climate scientists and more collaboration especially. So it's not that the insurance sector goes, so we want this, do it for us, and you come back and deliver something, but it's more like the co-design process that has been floating around for a while now, and it's actually has been shown to be quite successful. And in saying that, it's even Suncorp. So I was employed as a connection, as a link to the climate science community. So it's not that I will do all the work. It is more that I know who to ask, or that people know me and know they can come to me to say, hey, I have an idea, or what would you need as an insurance? And then we would work together trying to figure out, okay, if we have this hazard, how can we translate that into something that we can make a CAD model out of it, or that we can use it in a similar way as a CAD model. So with that, we can together then build an approach for a realistic and reliable risk assessment. And yeah, so in the end, with that, we actually managed to build a more resilient society, but also don't forget that insurances have money. And with money, we have a little more say in what policies are made, or what kind of, there's influence between insurances and building, not agreements, building standards, sorry. So there's that kind of influence. So if we want to change something, if we want to help out, I feel like it's insurances and also the finance sector are a really good way to approach this. So if you feel very passionately about something, come to me, we can chat and we can together try and, well, convince the insurance that this is really important, and also can do really exciting science, because that is basically in the end what we want to do, I think. And with that, I want to thank you.
Great, thanks very much, Nina. Really fascinating to hear how, yeah, you've changed from academia into private sector and how that's working.